let me correct. So here. So this would be. Hey, it doesn't work. Okay. Okay, this should be the same sheaf as above. So, right, and W is everything in the left. So this is defined by starting from this object here and like pull, push, pull. And essentially what we need to show is that push forward and push forward commutes with nearby cycle if we define everything over OC. So now let's do this over spot OC, where OC is C is the like this completed algebraic closure. And then actually everything here has the version over OC. You can define it. I mean, if you ignore if you only consider the upper half part, then everything is defined over OC.
Sorry, should pi quiz treatment have to start in another order?
Pi quiz, sorry.
Oh no, sorry, I was confused.
Okay.
Ignore me.
Okay. So we have this similar diagram of the small diamond associated to the Shimura variety, maps to the analytic Stuka and mu inverse. And then it maps, there's also a covering here, Stuka. And also maps to some, okay, let me not write this now. So here, we call that this is something like an untilt and a torsor over, a G torsor over the Y curve together with like a modification at untilt bounded by mu. And this is defined to be the same data as sharp E and this isomorphism, but adding a data that so that E will restrict to the S. S is a Cartesian divisor inside YS, and so this is a torsor of J GFP, and then we ask that we can take its reduction to the Lavie. And then take it. So we add a UL reduction of this torsor over the special fiber, and then this will be a L mod UL big diamond fibration. And there's also a map to the, we have, it's no room, okay. Anyway, but it turns out that this is not the correct morphism to consider because we want to show that something is compatible with nearby cycle. Then we need this to be a smooth map to pull back, but this map doesn't look like a smooth map, right? The fibers are the Igusa schemes, which has different dimensions, so it's better to consider the following object. Define this restricted Lucas mu inverse over spot OC by sending S to the following data. So it's an untilt S sharp. Let me check the formula. So, okay, so untilt and two torsor E1 and E2 of G torsors over the completion of S union of S sharp. And and an isomorphism E1 restrict to this. So this is really, if I just put things here, then this is just the Billingson-Drinfield F1 hack stack. But we can add in data that so E1 if we restrict to the completion of S is isomorphic to the pullback of E2, restrict to S sharp. So S is over characteristic P, so there is a forbidden on it. So this defines some pro-arting stack, and there's actually also a truncated version, and to make things really an arting stack. But let me ignore this. And so there's obviously a map from, like we have Shimura variety maps to the analytics Lucas, and the maps to this restricted Lucas. Oh, sorry. So this the definition of restricted Lucas is motivated by the work of Genius and Fork, where they do have similar constructions over function field. And there's also truncated versions, and here I can also define the same cover on the restricted Lucas by adding a reduction at the p equals to 0 point. And then this is still Cartesian. And here it also has a map to this hack stack, maybe to the hack stack for the Ihara level. Okay, that's the, so maybe just Billingson-Drinfield hack stack, which classifies, so we have an amplitude and two torsors that are like I-plus torsors over S union S sharp completion together with an isomorphism will restrict to okay, away from S sharp. So this is the picture, and so this map essentially forget this additional isomorphism between the forbidden pullback. Forget this isomorphism over the completion of the p equals to 0 part. And you mean here? Or here? Yes, sorry, yeah, that's right. So this is also bounded by mu inverse. Thanks.
You already said this, but what does S hat mean?
S hat is the completion of OYS along the Cartesian divisor S. So in this case, it's just the weight vector of R if S is RR plus.
And then S sharp would be like a beta round.
Okay, S sharp height is the completion of at S sharp, which is beta round. Plus, yes, thanks.
And then when you put a tilde over the entire Stuka, does that mean you've given the E's an I plus structure? What does the tilde over Stuka mean?
Tilde means you add, it's like this. So like this, so you have the torsor, and you put a U reduction of the special fiber of the. Yes, you can do the same thing for restricted Lucas. Actually, okay, I mean, yes. Actually, restrict Lucas refers to the truncated version of this stack. But I'm just, okay. Right. Actually, you should put some truncations to make this really a finite type some arting stack. And okay, now, so by construction, this CV, okay, sorry, time first. So over, if we bastion everything over spot C, then this picture become much easier. So we still will have the good reduction locus of the Shimura variety, SH. And maps to Shimura over spot C is just the flag variety quoted by this group, right? And then this is kind of to have this part, this flag variety of L and the Harris action of GZP and with a flag. Okay, and then the restricted Lucas here is just the B1 plus Avogadro-Grassmannian times the point, the Casimir stack of GZP. And now here, what is this? This is just a hike G less than equal mu inverse times the flag variety quotient by this group. Okay, and finally this map maps to the hack stack times the diamond associated to this Affen hack stack. Okay. And so here we can put a sheaf that you can put the Satake sheaf as mu inverse box tensor with the sheaf F, where F is like what we start from. S is is from this Delinostic induction of this object. So, and then we know that this ZV mu inverse convolution with F is just the nearby cycle of this Satake sheaf box tensor with F. This is only by definition. And so what we need to show is that we have something here, and take a nearby cycle, and then pull, push, pull. It's equals to you first have something here, and pull, push, pull, and then take a nearby cycle. So essentially, this is a commutation of nearby cycles. And if you check this, so this map is like some kind of pro-unipotent map. So pull back along it commutes with nearby cycle. And this map is an L mod UL torsor fibration. So it's a proper map composition with a T torsor. And push forward along it also commutes with nearby cycles if you restrict it to monodromic sheaves. So this is like proper plus a T torsor, T diamond torsor. So push forward along this also commutes with nearby cycles. So the key is to show that pullback along this map also commutes. Pullback along this map also commutes with nearby cycle. And then this is like a key result here. So input. So this map from Shimura variety to the restricted Lucas is some kind of smooth map. So this is not really, we cannot show that this is really cohomology is smooth now, but we can show something that is enough to show that this pullback is commutes with nearby cycle of this sheaf, right? So, and I think I don't have time to explain how to prove the smoothness, maybe. So let me just end the proof here. Okay, so now we have finished the proof of the local global compatibilities over SOC. And there's also, so for example, here we show that over the dynamic fiber you have the semi-porosity result if Shimura variety is proper. And actually we can do more over the special fiber. This is proved in a previous work with human, that this analytic, this algebraic Igusa sheaf always lies in the co-connective part of the sheaf on ISOC if you use this exotic T structure defined yesterday by human. And the compact support version also always lies in the connective part of the category. Maybe okay. So this works without the assumption that Shimura variety is proper. So if it's proper, then these two Igusa sheaf are identical. So then the Igusa sheaf will lie in the heart of the T structure. And so let's then give a sketch of this. So still, in this case, we have the pre-crystalline from Igusa stack to ISOC. The fiber are really just so fiber of pre-crys is really equals to the perfect Igusa scheme associated to B. And then you can do some funny things. We need to check, for example, this IB upper shriek of the compact version of the Igusa sheaf. It should lie in the connective part of GB representations. But then you can play with adjunctions and base change to show that this is actually computed by the compact support cohomology over Shimura variety. Maybe KP. Actually, any level works. Maybe let's take a Ihara level, and then have F star of the constant sheaf, where F is the map from this to the Shimura variety of say any Ihara level. This is by some formal nonsense again. Check this using the definition. And then there's a non-trivial input. So we have the following diagram. We can take the minimal compactification of the Shimura variety of special fiber, and then there's also a so-called partial minimal compactification of the Igusa scheme. So this is constructed by index. In the whole step case, this is constructed also in the work of Shenkai Mao. And we have the following maps. We call this F mean. And so in the work of Shenkai, he also showed that this Igusa scheme is well positioned, which means that essentially it intersects with the boundary of the Shimura variety, like intersects properly and transversally something. So as a corollary, we know that we can. So we have lambda if we do a star push forward along F and then J shriek push forward, then this is equals to first take a J lower shriek push forward and then take a F minimal star push forward. So if you plug in this in the formula, we get that this is isomorphic to the cohomology of the Igusa B minimal compactification, but the sheaf is the lower shriek of lambda. And now we can again use the result of Shanghai that this KB minimal compactification is affine of dimension 2 row nu B, and also the part without compactification is smooth of dimension 2 row nu B, and I mean limit of smooth varieties. So then again we win by arcing vanishing. This cohomology of okay, and so then by definition this means that this compact support Igusa sheaf lies in the connective part of the T structure. Okay, and other thing follows from duality. Let me check. And okay, now now that we have two versions of local global compatibilities that have exactly the same form, so you may ask if this is really the same formula. And it turns out that there is a comparison between these two formula. So recall yesterday Ian constructed this functor, this comparison functor I Lawrence by Ian Gleason, Hamann, Ivanov, Lorenzo, and Zhou, that there's a canonical equivalence from sheaf on S of G to deep on G, assuming that lambda is torsion. And okay, so let me recall this formula. So the analytic formula is you take this Igusa sheaf, apply a Hike operator, and then start pull back to the neutral component. And the algebraic formula is you again have some sheaf and take a Hike operator and then shrink pull back to the identity component. And it is showed in Ian's talk that you can do upper star pullback. This corresponds to upper shrink pullback here. So one of the three things are compatible. So now then actually we have the other two things are also compatible. So theorem of. So if we start with a V in rep G hat, then the following diagram commute. We can take the tame Shimura, tame part of the category, and we take the Hike operator here. And then we have a fully faithful embedding by using composition of psi and okay, into D bound G. And we also have a Hike operator here, and then this will be a kind of commutative diagram. And the other thing is, so this is the fourth part. Second part is that we have this analytic Igusa sheaf, and we can apply this. Have this algebraic Igusa sheaf, and we can apply psi to it. Then this will be isomorphic to the analytic Igusa sheaf. Okay. And yeah, I don't want to explain the proof of this, but just a direct quick corollary is that we know that the analytic Igusa sheaf also satisfies semi-perversity. Right? Because we know this for the algebraic version, and this functor is T-exact, so. Okay.
So I forgot, but was this known only in the proper case before?
This, yes, for analytic, yes. Yeah. And also, because for PL type, it's kind of subtle. Because you really have 4 Igusa sheaf on the analytic locus, you can, so you have 2 Igusa stack here. Oh, sorry. And you can push forward from this to the bond G. You get 4 Igusa sheaf, and I guess it's for PL type case, if you push forward from the this big version, then it will also satisfy semi-perversity. It's only put by Linus Hamann and Xing Li. But for this one, I guess it's only known for compact varieties. Right, that's all I want to say about the local global compatibilities, and maybe the rest of the time I will explain some applications of these formulas. So yes, for smaller, yes. And so the first application is to torsion vanishing. So, okay, and well, we can take lambda coefficients to be either alpha bar, but of course we can also take QR bar. But then it's not we call it torsion vanishing. But anyway, so so recall that yesterday, so Jim mentioned the following theorem that so assume L is like not too small. I don't know, it's like greater than a constant number. Then we have the tame Langlands functor, ISOC to in co nilpotent single support on log tame. And then if you projection to the in the perf category, then this combination is psi. Okay. It's called steep psi tame. Then this is the T-exact functor, where the right-hand side you put the exotic T structure, and the left-hand side you put the good filtration T structure.
Is P different from L?
Yes. Yes. Well, I guess all this summit here is always different from L. Where are we? Okay, so a quick corollary of this is that we have this Ihara-Whittaker representation, which is defined to be common induction from the proper Ihara to G, and psi, but psi is some this kind of additive characters that are non-generic. Maybe say here the GQP is ramified. So it's quantitatively, so we have a Whittaker datum. Then also with the assumption that Gx is of Hodge type. And what else? Okay, then we know that the home from the Ihara Whittaker representation to the cohomology of this is in degrees. D to 2D, where D is the dimension of the Shimura variety. And also you have the other one for the compatible cohomology. Okay. And another, like, what it's saying is that, corollary is that if pi is a irreducible depth zero representation of the GQP, so that it has non-trivial Whittaker model, home from the Ihara Whittaker to psi, to pi is non-zero. So, okay, so Ihara Whittaker representation is really the depth zero part of the Euro Whittaker representation. So this is equivalent to say that pi is generic in the sense of the Whittaker model is non-zero. Then, if pi is a subquotient of the cohomology, then I should be greater than the dimension. And if it's a subquotient of the cohomology, of the compatible cohomology, then I should be less than equal to D. Okay, this is just simply because that your Whittaker representation is a projective object.
In the first corollary, is there a D1 there?
D1?
Well,
This comma, this is comma. Okay. So in degree D to 2D. And this is in degree 0 to D.
So in this corollary, if there's a homomorphism, then it's automatically in the same parts, is that right?
Yes. And this is confirmed some cases of the conjectures by Terhisa and Sbu. So this is some subcases of the conjecture of Koshikawa-Shin.
Maybe the generic case was attributable to many people before.
Really, I don't know.
Many experts have been.
Okay, anyway, so.
Probably I don't do that.
Yeah, but I'm just write it in this way. So, well, they have a much more general vanishing conjectures than this, but anyway. And so, why is this true? I mean, proof of this corollary, corollary A. Okay, so if we plug in this formula, we know that home from Ihara Whittaker to the cohomology is just home from so Ihara Whittaker I1 star to this TV acting on the Igusa, algebraic Igusa sheaf, maybe tame part. And so if a plus to apply this fully principal functor L, then this will become home from inside in the Koch nupe of log tame. From the structure sheaf to, because this will correspond to structure sheaf, and to the V mu tensor with the L applying to this algebraic Igusa sheaf. But because you are homing from O, actually this also factors through the cos Langlands functor. So this is really the sections on log t LG QP of the V mu tensor with this steep side thing of this object. And then we know that this is T exact, so together this is in degree greater than or equal to 0. And although it's in a different T structure, but it's still enough to show that this is in degree 0. Okay. And well, sorry, also we here we had a shift here, so we get that this home is in degree greater than D. Okay. And the other one follows from duality. Right. Okay. And there are also other versions of torsion vanishings that says that if you localize the cohomology of Shimura varieties as some generic part of the Bernstein center, then it should also concentrated in the correct degrees. So this also follows from this. We can also say something about this. So we can define. So if phi is from V group of QP to the Langlands dual group lambda, if it is a semi-simple L parameter, we can consider its capital support. Like phi m. So that so this is the supercapital L parameter, and phi is equals to sorry, m is la v, and phi is equal to the computation of m with the embedding up to congregation. Okay, this is always such a supercapital support, and we define that phi is called generic, but maybe so Linus would like to call this vaguely Langlands Shahidi type. And I forgot, so how do you call it? Generic, good. And so if the following conditions holds, so we can consider H2 of the V group cohomology on the following space. We can take the algebra of J quotient by the algebra of M, and then take the phi M part. Like so, this is trivial where so this G hat mod M hat carries an adjoint action by LM. The conversation with phi M, you get an action of the V group on this vector space, and we ask that this H2 vanish. Okay, and if, for example, if phi is a parameter for GLN, and assuming that it's aramified and semi-simple, so it is a direct sum of characters. So phi are aramified characters. Then this generic if and only if this phi is I is not equal to phi j up to twist by 1 for any I not equals to j. Okay.
So this is still true even if you don't assume phi I is unmodified. If it's just a character, maybe the same condition.
Yes. 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 And so this will define. So we have this log LG QP. Sorry. And this has a map to the corresponding line, maybe just the spec of the spectral Bernstein center. And inside here, this is open subspace of generic Langlands parameters. This is an open alpha n subspace, and we call this fiber product log generic of the stack. So this is open substack. And why is this useful? Because we have the following proposition. It says that we have a nilpotent single support condition here. And if we restrict to the generic part, the generic part of the L parameter stack, then this is actually the zero sections. So this inside the shifted content bundle of so inside the singular stack, singular space of singularities of this. And so you can remark that if this lambda is QR bar, then this log J generic is actually smooth. And then, so the nilpotent single support here is just trivial. But if lambda is modular coefficients, then sometimes this stack is far from being smooth. So if lambda is modular, so there's sometimes that this stack is even maybe it's non-reduced. So there's no smooth point on this stack. But so what this thing is that this nilpotent single support only lives over the semi-simple direction. So if you intersection with the nilpotent direction, this is vanish. So, but anyway, but the corollary will say that the nilpotent single support log generic LGQP, this will be isomorphic to just in the perf. Good. And so, right, so now we can get something, another corollary. So if you have this L psi tame, we can take its generic part, which is by definition this category localized at this spec Z tame and spec Z tame generic. Also not spec, maybe QCO. Spec. Anyway, take the localization at this generic part, and it has a map to in the Koch nilpotent log tame generic LGQP, and this is still a fully faithful embedding, but then this is isomorphic to in the perf log tame generic LGQP. So in this case, really this C psi functor and alpha psi are just the same functor. So C psi is T exact, implies that alpha psi is also T exact. At least the generic part of this T exact. Okay, and the consequence is that so sorry. Okay, so the consequence is that if this V is a tilting G-hat representation, which means that V has a filtration by both both wire modules and Shor modules. And a filtration by Shor modules. Then this Hecke operator TV will restrict to the tame part, the generic part. This is T-exact. With respect to the exotic T structure on both sides. And as a corollary, we know that the cohomology is of a Shimura variety. If we take the tame part and then tensor over the spectral center with the spectral center tame, so this is just a subspace of where the generic, Hecke action is generic, then this is in degrees D to 2D. And similarly, you have the same statement for compatible cohomology. Okay. What else? And so this has there's a long list of people doing similar results. Let me just list them. So first, the first this kind of results is put by Kariani and Scholze. And then there's a Terakisa, Kochikawa. And also there's the work of Linus Hamann and Siying Li. And there's also the work of myself with Xingwen. So all prove similar results, so similar event, but with less generality, I guess. For example, this Kariani Scholze proves this case for the case when the Shimura variety is PL type, and locally the group is the product of GL and QP. And then Terakisa used a different way to prove this, and Hamann and Liu proved this for some more general PL type. And here with this work, we prove this kind of vanishing for hyperspecial level in the group of abelian type. And now this can be done for type 0 level. Okay.
So in the first three groups, there's no thing.
Yes, but they need to restrict to this principal series.
Oh, so even
I mean, they can restrict to some.
Neither weaker nor stronger.
Yes.
Neither weaker nor stronger. Because they allow the principal series arbitrary depth.
Yeah. Yes, maybe right. So this is for principal series, and this is for ramified Ihara level, so parahoric level. So okay. Anyway. Let's see. So I'm planning to talk about some explicit computations and to show some kind of level lowering of modular forms using this formula, but it seems that I've run out of the time. So.
10 minutes because of the technical problem.
Ah, okay. I mean, okay, but it's still not enough for me to finish this part. So.
You can say something fun.
Yeah, you can say something.
Yeah, I'm gonna say something that maybe.
If we run out of time, we will ask questions.
This is called measure principle or level lowering. So essentially, this is not a new result, of course. This is proved by Major and Ribbett, and 40 years ago. And it says as following: so if you have a f as a modular form of a level, say, gamma 0 p, np, that is new at p, then you can get some global Galois argumentation to Q-bar coefficients. And then the thesis is the following. So the theorem of Mazur and Ribbit. So Mazur assumes that Q is not 1 modulo L, and Ribbit puts this in more generality. So it says that if the reduction of rho is irreducible, so we can have the reduction from, or maybe we should put a Caspidal modular form here. If the reduction of this to FL bar is irreducible, and essentially some other meld assumptions, then if this rho F bar is unramified at P, then there exists other modular form G of level gamma not n. So no level at P, hyperspectral level at P, such that the rho F is isomorphic to rho G. Okay. But it says that, okay, so rho F itself is not unramified at P, because at P it will be the Sternberg representation. So rho F at P, the Frobenius will be like a Q like this, and the Tim generator will be this Jordan matrix. But it may happen that after you take a residual mod L, QSP, yeah, sorry. It may happen that after you residual mod L, then this nilpotent element becomes trivial. So in this case, this is that you can find another modular form that has no level at P, such that there is really congruence to each other. And so I would like to explain how to prove this under the Mazur's condition. So prove using CLLC under the assumption that L is not congruent to Q minus 1. So Ribbit's proof is some very clever ideas, like they find some auxiliary prime Q and do force lowering, so raising, lowering. So. Yeah, thanks. And let me see if I can do this. But because there's no time, maybe let me just assume that Q is not, right, this is Mazur's case. Let me just assume that Q is not plus or minus 1 mod L. This is, so this is called Banel, and then the representation theory and the stack of L parameters looks very similar to the characteristic 0 case. And then what we have is we can have a modular curve of level gamma 0 Pn, and another one is a modular curve of level gamma 0 n. We call this x prime. And yeah, so what we have is that so this rho F bar will define the maximum ideal M inside the global Hike algebra, acting on the cohomology of X or X prime. And we can take localization of this to cohomology at M, and you can get the following formula. So H1 of X, this coefficient lambda is null, so lambda is FL bar. So this is equal to home from, so V mu inverse tensor with the coherent Springer sheaf. I'm using the formula before with some algebraic, so with some Igusa sheaf, and just write F. So this is equals to L applied to the Igusa sheaf. And another one is given by Hom V mu inverse tensor with the structure sheaf on the ramified locus with F. And so okay, again we need to draw this picture. So log tame, maybe tame QP localized at M. So localized at this particular parameter where Frobenius is P1 or maybe P. This looks like the crossing. Okay, and with the vertical GM action. And so we will contract the vertical line to a point and act trivially on the ramified locus, the Sternberg locus. And the coherent Springer sheaf in this case is the structure sheaf on the ramified locus, direct sum with the structure sheaf on the unipotent locus. Yeah. Okay. So what it's saying is that this tensor product. Okay, sorry. So we want to. So we know that this rho F bar is ramified at P. We want to show that this hyperspectral level, the cohomology is also non-trivial. Okay, so this is all we need. And you can do the following. So V mu inverse tensor with the coherent Springer sheaf is O ramified 1, O ramified minus 1, O unipotent 1, O unipotent minus 1, right? And if you so by definition, this S1 is of the form pi star of structure sheaf on log B unipotent. So log B unipotent is something like you have an element X, A, B, C, which is upper triangular, and an element Y that is it's like 1, 1, D, satisfying that X, Y, X inverse is Y to the pth power, quotient by B hat. And so we have the following exact sequence. So we have O log B minus 1 maps to this V mu inverse tensor with O, then that maps to O1. Okay, this is because if I have a limitation, if you restrict to B, it will create a filtration. And there's also a map D sends O B unipotent to O minus 1 log B unipotent. So what we have now is that if you plug in this thing into the formula, we get a filtration on the cohomology of modular curve. Essentially, you have maps to home from pi star O log B 1 minus 1 to the Igusa sheaf, and Igusa sheaf, right? Because right, I'm pushing down everything here and get such a distinguished triangle. And then you also have, it turns out to be an exact sequence, short exact sequence. And you also have a map D here, which is equal to the monodromy action on the cohomology. So this is really given by the maybe tau minus 1 action, where tau is the time generator in the wave in the while group and in the V group. So essentially, this condition that rho f bar is unramified will implies that this map, let me call this N is not an isomorphism. This N is not an isomorphism. Right? Because essentially this cohomology is an extension of rho f bar. So if we know that it's unramified, then right, there needs some argument, but I'll just like this. So what we know is that the cone. So if we take home from the cone of pi star O log B 1 to pi star O log B minus 1 to the Igusa shape, this is non-trivial. Right, this is just sorry, what's y? It's D. This is just this map N here. And then if you compute the cone, this is really, so pi star. So this is a two-term complex. H0 is equals to, maybe we call this C. So H0 of C is given by pi star of O log B ramified, shifted to minus 1. And H minus 1 C is given by log B ramified, shift to 1. And so ramified, of course, the ramified stack is just B mod D, and it maps to pi G mod G. This is log G ramified. Wait a minute, you are before. And again, we have a similar solid sequence of this triangle. So pi star O B mod B minus 1 maps to pi star V mu inverse times O B mod B 1. Okay, and this is just O G mod G, but 2 copies of it. Tensors with V mu inverse. Okay, so the upshot is that we know that this cone maps to F is non-trivial. This implies that at least, so one of the home from O pi star O B mod B to F, and the other one. So one of them, they are not, at least one of them is non-trivial. So it's non-trivial. But somehow here we know that this object is only given by the extension of this two. So recall that. So if you apply home to the Igusa shift to this discrete triangle, this will imply that home from pi star O minus 1 to F maps to H1 of the X prime. 2 copies, then maps to home of. Right. And then we know that these two are non-trivial. That will implies that the middle one is also non-zero. This is very. So this, okay, I know it's a lot of details that need to be filled, but let me just stop here.